Okay, and we're back. I got cut off by Zoom during the last one, so this is now going to be yet another video. But that's all right, actually. I hope it cut off in a good place so that we can kind of change topics here. And we're going to talk about trends in the periodic table. Okay, so we're going to use everything that we've already talked about to figure out why these different trends exist. Why do we see the trends that we do see on the periodic table? And you can hopefully get used to sort of picking out what the trends are, picking up on what the trends are, and then being able to use them. Okay, and you know, like when you're trying to decide, well, which of these ions is bigger and smaller, bigger or smaller. How does that distance affect its interactions with other atoms? It's all going to go back to the different energy that's involved in the interactions, like everything else does. But let's start working through what some of these different trends are that we are seeing. And we're going to start by talking about atomic radius, all right, which is it's in the name. It's the size of the atom, okay? So we're talking about what the actual radius is from the center to the outer limit of the atom. And we see a trend in the size of the atomic radius in two directions. We notice that as we move from left to right across the rows, that we see, that we see smaller atomic radii. Okay, so let's think about why this is. We're going to have an effective nuclear charge, as we saw before from our last example, increase. Okay, an effective nuclear charge increase means that you're going to have a stronger attraction between the electrons and the nucleus. Right, so the positive and the negative charge is going to try to draw together more the higher the effective nuclear charge is. The stronger the attraction between the positive and the negative charge, the smaller the radius is going to be, because the two things are going to try to get closer and closer together. So the larger the effective nuclear charge, the smaller the radius is going to be, and we see the effective nuclear charge increasing from left to right. As we move down the columns in the periodic table, we are adding energy levels to our atoms, okay? This is maybe the most practical trend, because atoms that have fewer energy levels are going to be smaller. At the more energy levels that we add onto our atom, the larger that they get. So as we move down columns, we're going to see an increase in atomic radius. Okay, those are our main trends. How are we measuring the atomic radius? Well, there's two different measurements that we have to look at here. Okay, we have what's called a van der Waals radius, and this is a non-bonding radius. All right, and we'll talk more about van der Waals forces in chapter 11, but we should have an idea of what they are right now. That's a non-bonding radius. So an example down here is something like krypton, where two krypton atoms are not actually bound together with a chemical bond, but they do have a van der Waals attraction between them, and that is, it's still an attractive force, even though it's not an attractive force with the strength of an actual chemical bond. Okay. Our other factor is going to be the covalent radius, and that's the bonding radius. Right, so that's, for example, here the chemical bond length between two bromine atoms. That is the covalent radius. So when we take atomic radius values, we're going to be taking average radius values of atoms. Okay, this is going to be based on many measurements over many elements and many compounds, so that we can get numbers that are consistent and applicable on a large scale. So we talked about the radius decreasing from left to right. This is because we're adding electrons to the same valence shell. Okay, so the more electrons that we add to the valence shell, the more strongly they're going to be attracted to the protons in the nucleus. And they're going to just get held together tighter. Okay, that positive and that negative charge are going to be attracted to one another. Okay, and then as we travel down the group, we're going to be adding onto our principal energy levels. So the further away a particular energy level is from the nucleus, the less attracted it's going to be by the positive charge in the nucleus. So that effective nuclear charge value, you know, it's going to be, it starts to get like less, it gets diluted the larger our atoms are. Now transition metals, once again, they're going to always bring something a little bit different to the table here. We are going to notice that the size of our atom is going to be related to the distance that the valence electrons are from the nucleus. All right, so our atomic radius is going to mostly be determined by our period value, not by our group number in terms of transition metals. As we move across the D block of elements, we're going to see that the radius doesn't really change. And that's because we still have this NS2 value out front of all of our D electrons. And that effective nuclear charge is going to be the same for all of them. Okay, so this is a slightly modified visualization of the atomic radius trend in the periodic table. If you look at the one in your textbook, you'll see that they do it a little bit differently, but I think it's nicer to have things drawn out so that we're describing the same situation in both of them. So I have this listed from left to right as decreasing radius. So we have big to small. And then I have over here from the bottom to the top is also decreasing radius. Okay? That means when you set up your trend graphs with two similar axes, so both of these are decreasing values, then you can find an overall trend for that particular property that we're describing. So I can say, if I put one end of my arrow here by rubidium and I trace it and I make an arrow all the way up to helium, I can say from the main group elements point of view that I'm going to have an overall decrease in atomic radius as I move to the right and as I move up. So whenever I'm comparing two different elements, if I was wondering what the atomic radius difference between like carbon and nitrogen was, I could use my little trend line to help me figure that out. If I was trying to compare phosphorus and nitrogen, I can do that as well. Trends in ionic radius are a little bit different than your neutral atoms. And we have to think about what is being gained or lost by the atoms when they're forming ions to make the size values seem reasonable to us, okay? In general, our cations are going to be smaller than our neutral atoms, and our anions are going to be larger than neutral atoms, okay? And also another good generalization is that cations are going to be smaller than anions, with very few exceptions. Okay, we're talking about the examples that are listed here. These are the biggest cations, and these are the smallest anions. So that's why that's maybe a little bit different. This is a visualization of them, and it's good to keep going back and and looking at this when we're like working through these examples, so that you can verify for yourself the concepts that we're talking about. For anything that is isoelectronic, that means that they're going to have the same two things that are different atoms, different ions, but they're things that are going to have the same electron configuration. When you have isoelectronic species, when you have a larger positive charge, that cation is going to be smaller. Okay, so if you have a list of isoelectronic species, and you have a cation, a neutral atom, and an anion, and they are all isoelectronic. Your cation will be the smallest, your neutral atom will be intermediate, and your anion will be the largest. All right, we have to talk a little bit about the whys of this, and we're slowly getting there. So when you're forming your cations, you're obviously removing your valence electrons, right? So when you remove your valence electrons, you are literally making your atoms smaller, right? Because you're removing a principal energy level. So if you have a smaller atom, then your new valence electrons, those are closer to the nucleus. And things that are closer to the nucleus get pulled in tighter. Okay, so kind of squishes the cation in, makes it a little bit smaller. All right, I said some of this right now. So that's the shrinkage here that I was talking about. In general, when we're going across a period, when you, again, have isoelectronic cations, the cations are going to get smaller. When you're forming anions, on the other hand, you're going to be adding electrons to the valence shell. Okay, so you're physically making your atom larger. You're adding, I mean, you're building onto it. You have to think about it in terms of like adding and removing building blocks. So say that your atom is like, I don't know, imagine like a little cube of Legos that you built. All right. If you take away 4 Legos from your building, it's smaller now. If you take another handful of Legos and build onto it, now it's bigger. That's what's happening with your ions as you add and remove electrons to them. All right, so these are just some size differences that you can see. All right, and it's good to compare them. It's good to notice the numbers here. These are this is the distance that's measured in picometers. It's also very interesting to see the difference between a neutral atom and the corresponding anion. Like those values get much larger. Okay, when we're moving from left to right between the neutral atoms, like if we're comparing selenium to bromine here, the decrease is not that large. It's 117 picometers to 114 picometers. But when we're comparing the difference between a selenium neutral atom and a selenium anion, it's 117 picometers to 198. Like that's fairly substantial. So take a look at this question and see what you think about it. In the previous sections, we've seen how the number of electrons and the number of protons affect the size of an atom or an ion. However, we have not considered how the number of neutrons affects the size of an atom. Would you expect isotopes, so in this example, we're talking about C12 and C13, to have different atomic radii? So try to reason that out. Okay, now a neutron has no charge. So if we're imagining that the size of our one of the factors anyway, that plays into the size of our atoms and our ions is that charge and that attraction of opposite ions, then we should probably be able to reason out that adding or subtracting neutrons to an atom isn't going to have an effect on the size or the charge of the atom. Okay, our next trend we're going to talk about is ionization energy. All right, so what is ionization energy? That's how much energy we are going to need to remove an electron. Okay, so the cost of ionizing an atom. That's what ionization energy is. So we have an example of the ionization. This is a generalized, this isn't a particular element, but we have a monoatomic gas here, okay? And when it undergoes its first ionization energy, you end up with a +1 gas and a free electron, all right? A second ionization energy is when we take the product from the first ionization process and now we remove an additional electron from it. Then we get a product with a +2 charge and another electron as a product, all right? So when we say first ionization energy, we're literally talking about the energy that is required to remove the first electron from a neutral atom. The second ionization energy is the energy required to remove an electron from a +1 cation. Okay. Now, a fun fact is that the larger the effective nuclear charge is on an electron, the more energy is going to be required to remove the electron, right? And that should make sense because a large effective nuclear charge means that the electron is being pulled on very hard by the nucleus. So it's not going to want to give up that electron. The farther the electron is from the nucleus, the less energy it's going to take to remove it. Okay? So with those two factors in mind, we can visualize a trend. Our first ionization energy is going to decrease down the group, okay? Because down the group, when we're moving down a column, our atoms are getting bigger and bigger. As atoms get bigger, it's going to require less energy to remove electrons. Our second statement explains this trend, that first ionization energy generally increases across the period because our effective nuclear charge increases across the period as well. And if we ever forget whether our effective nuclear charge is increasing or decreasing across the period, go back and solve for it. Pick one of your rows on the periodic table and calculate the effective nuclear charge of something in group 2 versus something in group 7 and compare them. And then you'll be able to remember the direction of the increase of nuclear charge, of the effective nuclear charge. Okay, so this is the way that your textbook draws out your tables, where they do opposing. I don't know, they do the opposing axes. They have increasing down here, they have decreasing over here. As long as you can remember the trends, that's fine. But I do recommend that you maybe orient the arrows and the axes so that you can remember the trends in terms of one diagonal line. Like if you drew an arrow from the bottom corner here from cesium up to helium, you can draw that line and say that that is increasing ionization energy. But it's up to you. Here are some explanations of our trends in first ionization energy. And we really have talked about some of these already, so we can kind of run past them. The strength of the attraction is related to the distance. So the bigger the atoms are, the less attracted they're going to be to the nucleus. or I guess that's the second part here. The larger the effective nuclear charge, the less the attractive force is going to be. So those are the two main ones. Yeah, I mean, we pretty much covered this. Our atom's first ionization energy should get lower as we move down a column because of size. Traversing across a period increases effective nuclear charge. That means that the ionization energy should get larger across the period, and it does. Our nonmetals do not like to lose electrons as much as our metals do. So knowing what you do, determine which element in each pair has the higher first ionization energy, if possible. Okay, so pause, try that now. Okay, so we should be able to see when we're comparing aluminum or sulfur, aluminum is further left than sulfur. So sulfur is going to have a higher effective nuclear charge. It's going to have a higher ionization energy. When we're comparing arsenic and antimony, arsenic has a lower period number. So our ionization energy decreases as we go down the column. So arsenic is going to have a higher ionization energy than antimony will. Okay, I want you to remember these two exceptions for this, and this has to do with some electron configuration stuff. Your exceptions are from group 2A to group 3A and group 5A to group 6A. This is where we don't see that first ionization trend increasing from left to right. Okay, and this is because when we have something, for example, that's in group 5A, if we have to ionize the nitrogen, we need to break up this half full sublevel. See how it's exactly perfectly halfway filled. We have 3 upspin electrons in there, nothing is paired up. That's actually very stable. Now, to pull an electron out of here, that would require more energy than simply taking this extra electron from group 6 and ionizing that electron. But those are your two exceptions, okay? This happens from when we're comparing group 2A to group 3A and when we're comparing group 5A to group 6A. Other than that, that trend holds. So what have we not talked about here? Removal, yep. Okay, this is what I want to talk about down here in particular. You guys can read the rest of this. But you're going to notice when we look at the table on the next slide that there is an increase, right, when we're removing each valence electron. And there is a pretty low and regular increase when we're removing valence electrons. As soon as we run out of valence electrons to remove, all of a sudden the number gets enormous and there's a huge increase in energy when we hit the core electrons. So you can actually use an ionization table to tell what element you're looking at, because you can tell the number of valence electrons it had versus core electrons. All right, so for example, if you look at your periodic table, we know where each of these elements sits on the periodic table. So sodium is in group 1. So notice the ionization energy of the first electron is only 496 kilojoules. If I wanted to remove another electron from sodium, that is going to cost me 4,000 extra kilojoules than that first electron cost. Right? That's a substantial increase. That's how you know that the first electron was a valence electron and anything else is a core electron. Magnesium is in group 2. So my first ionization energy for magnesium is 738. My next electron is about twice that. That's fine. That's another 700. If I want to remove a third electron, 7,730 kilojoules. That's a huge jump. So that's how we know that magnesium has 2 valence electrons, and then we're into the core. Okay. If we look at something like phosphorus, that's in group 5A. So we know we would expect it to have 5 electrons, 5 valence electrons. Look at my numbers here. This is my first electron, second, third, fourth, my fifth, and all of a sudden, if I want to take off that 6th electron, 22,000 kilojoules. So when I'm comparing that, I'm like, oh, nope, that value right there, that's a core electron value. So this element only can have 5 valence electrons in it. So you can actually use that information to figure out the identity of an element. So looking at this example here, a second row element, so it's in period 2, it has a large jump between its third and its fourth ionization energies. What is the element? So if it has a huge jump between the third ionization energy and the fourth ionization energy, that means that it has 3 valence electrons, and that fourth electron is a core electron. So which of these is in group 3? It's boron. So that has to be the identity of the element. Okay, try this one. I mean, this is kind of a giveaway question, I think, right? Valence electrons are always going to be most important when we're talking about just anything to do with reactivity or bonding, because they're the ones on the front lines, right? They're our most loosely held electrons. They're the ones that are most easily taken and given away. The next trend we're going to look at is electron affinity. You're going to hear 2 terms that kind of overlap. Like we've talked about electronegativity already. Don't confuse that with electron affinity. All right, electron affinity is a little bit different, but it still has to do with how much a particular atom wants to pick up an electron. So, you know, there is like a similar theme to it. But this is an example of what that would look like, okay? It's the energy released when a neutral atom in its gas state gains an electron. So for example, chlorine gas, when it picks up an electron, it turns into Cl-, and then there's this activation energy, or not activation energy, electron affinity energy over here. Okay. Now, we consider this a negative value because your atom is going to release energy when it picks up an electron. And just like when we were talking about thermochemistry, whenever you have that release of heat or the release of energy, that release gets a negative value associated with it. The only real exception here is that some of our alkali earth metals and all of our noble gases, for them to pick up an electron, it would be an endothermic process, because it's not energetically favorable to like force an electron onto a noble gas that already has a stable and full electron configuration. Okay. Now, the more energy that is released when you pick up an electron, the larger the electron affinity value is. Okay, so you'd imagine something like a halogen would have a very large electron affinity. This trend, though, it's not as regular as the other properties that we've looked at. Okay, The only very steady trend that we see when we're comparing electron affinities is the alkali metals, because that electron affinity for those decreases as we move down the column. But it's not, that trend doesn't hold true for other groups. We do see a much more regular trend than when we're moving across the periodic table from left to right. Usually the electron affinity becomes more negative from left to right. And remember, we said that a large negative value means that it's releasing a lot of energy, right? So we have two notes here, okay? Our group 5 is going to be an exception to this trend only because we have an extra electron that's introduced in group 5 that we're going to have to do something with. And that extra electron is not going to fit anywhere into the orbital diagram nicely, if you want to sketch that out for yourself. For groups 2A and groups 8A, I think it's, in either case, it's pretty easy to see because we already have full sublevels, right? Because in group 2A, we have a NS2 sublevel. So we have a full S sublevel. In group 8A, we have NP6. So our P sublevel is completely full. If we added an electron to either of those sublevels, we would have to add an entire additional energy level or an additional sublevel, right? It would cost us energy for us to do that. The highest electron affinity of any period is going to be the halogen, because the halogens love picking up electrons and they release a lot of energy when they can pick up an electron. Notice that there's not even values for this because it's like, well, I mean, greater than 0 means that it has no electron affinity really. Okay, and then we have something here like nitrogen, because again, picking up an electron would lead to having to place that new electron into the orbital diagram that was already very nicely spaced out and energetically favorable. So that's the electron affinity trend. Next, we're going to talk about the difference between metals and nonmetals and the characteristics, or the kind of the metallic characteristic of our different elements. This is, again, old stuff that we've already talked about, but you know, it's good to remind yourself of it. These are the generalized properties of metals. These are the properties of nonmetals. Our newest addition from last time is that metals are going to lose electrons in reactions and become oxidized. Nonmetals will gain electrons and become reduced. We can actually look at the periodic table to determine the metallic character of a particular element. And honestly, this has much less to do with memorization. You can do most of this just by looking at your periodic table, okay? So when we say that something has metallic character, that means that it's hitting a lot of these points over here on the metal side, okay? It's exhibiting a lot of these properties. So metallic character is going to decrease from left to right across the periodic table. Now that should make sense because your metals are on the left and your nonmetals are on the right. So you would expect it to decrease from left to right. Metallic character increases down a column. All right, now again, if you look at your periodic table, and let's switch over and look at the periodic table here. If you come over to the right side of your periodic table here, okay, and let's pick one of these columns. So we're going to pick group 6A. If I move down the column, okay, I'm starting with a nonmetal, 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 metalloid. So now I've picked up a little bit more of a metallic property. And as I continue down the column, now I have metals. So my metallic character is increasing as I move down the column. Now, the other trend, if I move from left to right, I start with metals, and as I move towards the right, I enter into my metalloid territory, and then I move further into my non-metal territory. So my metallic character is decreasing from left to right. So again, you don't have to memorize this trend, you just have to look at your periodic table. Some basic characteristics of metals, they're going to have smaller first ionization energies. That's because metals, they want to remove their electrons. So to get rid of their, they have small first ionization energies so that it's easier to remove electrons from them. Nonmetals, on the other hand, are going to have very large electron affinities, with the exception of noble gases. Okay. Our metallic character should increase down a column because the valence electrons are not held as strongly. If the valence electrons aren't held as strongly, then we should be able to ionize them easier. Okay. And metallic character should decrease across a period because our valence electrons are held more strongly as I move from left to right. So I don't want to get rid of my electrons. I'm actually looking to pick up electrons. My electron affinity increases from left to right. So really, it's all very logical, the trends that we've listed here. I've just kind of like put together the trends of the important groups out of this. So we have the alkalis, the halogens, the noble gases. And we just have some of the real, the characteristics that stick out in each group, okay? For your alkali metals, which are your group 1 metals, your atomic radius is going to increase as you go down the column. So it's going to get bigger as you move down. That makes sense. Our ionization energy decreases down the column. That means that things at the bottom of a column are going to be more reactive than alkali metals at the top of the column, because it's going to be easier to remove the electrons from them. So they're more likely to react with other things. Very low ionization energies, easy to oxidize. Yeah, all that's true. Our electron affinity is going to decrease down the column. Our melting point is going to decrease down the column. Yeah, so take a look at those. If there's anything here that doesn't make sense to you in particular, definitely send me an email about it, because I'm hoping there's not much more I can really say. This is mostly like a recap here. Your halogens have a very high electron affinity. They're good oxidizing agents, which means that they are reduced. They react with metals to form salts because metals easily give away electrons. Reactivity increases down columns. With your noble gases, again, the radius will increase down the column. They have extremely high ionization energies. It's really not worth it to try to react something with a noble gas, except under extreme conditions. We often call noble gases inert gases for this reason. The melting point and the boiling point both increase down the column. All of the noble gases are actually gases at room temperature. And that's it for your trends, okay? So now we're going to move on to chapter 9.